Well, I'm going to be under a lot of trouble first of all because you've given me the wonderful privilege of spending some time with Peter Hook, who's an electrical science and principles specialist.
He is, yes.
Which I think we've probably got the wrong two from eFIXX for this one. But I'm going to put my hand up and go over there, and I'm going to take this over here. Looks remarkably like something that maybe my kids would have played with back in the day when we start.
My kids have still got them, I think.
Oh, have they?
Yeah.
Let's find out what it is with Peter. So Marcus has ducked out of this one and given me the electrical science and principles. I think I'm in safe hands, Peter Hook, because this is your bag, is it not? Nice to meet you, Pete.
Yeah, absolutely, Gary. Nice to meet you as well.
You've got some interesting stuff behind us, and it's certainly out of my comfort zone. This is more Joe Robinson than it is me. But you're going to walk me through the basics of the machines we've got behind us. Now, we often call them motors, but they're actually electrical machines,
Yeah,
aren't
electrical
they?
machines, yeah. So rotating machines. I think there's only one reference in the regs, BS7671, on rotating machines. So it's very short and sweet in our regs book. It starts to talk about the science and principles behind motors. How do they work? The concept of a squirrel cage induction motor is approximately 100 years old. So Nikola Tesla's invention, as it were. So paying homage to Nikola Tesla there.
Yeah, okay. And it's really interesting stuff. Now, this is the bit normally after the first term where we've done health and safety. Lots of colleges like to jump in to get rid of the science stuff and then sort of leave the Instech stuff towards the end of the year. Absolutely. So hopefully, as we release this video, this should be really helpful, not only to the people watching, but obviously to me as well, Pete. Shall we take a look?
Yes.
So first of all, address the buzzing noise that I can hear for me, Pete, because people are going to say it's buzzing, it's buzzing.
Okay, so very lucky here at the college. We've got a 50-volt three-phase transformer. It's an isolation transformer, so everything's under controlled conditions here. Yeah, having three-phase, so we can actually demonstrate the electromagnet for this stator, as it were. So hopefully we're going to talk about the concept, the science behind it, why it works the way it does. We've got a little model to demonstrate. But first, we're going to perhaps have a talk about a universal motor. Okay, so the universal motor works on the concept of slip rings and brushes.
Okay.
So on here, we've got the intricacy of the windings within what we call an armature. So there's a couple of differences between an induction motor and a slip ring and brush motor.
Okay.
Okay, so what we have with this is copper windings that go through this armature. And that's transferred either with a motor or a generator to some slip rings that run on soft carbon brushes. Okay, so there's actually a physical electrical connection between the brush and this rotating part. So the rotating part in a universal motor is called an armature.
Okay, and the brushes sit there, so this would be a three-phase one, wouldn't it? Because obviously
Yes,
three slip rings are on there, and they're in constant contact with the actual slip rings as we go all the way round, aren't they? There's no break in it.
No. So
why is that then? So just talk me through why that would have no break in it.
Okay, so it would these are line 1, line 2, and line 3.
Yes.
So in terms of this motor here, technical keyword here is rotor wound motor, rotor wound motor. Okay. So it works on induction, but not pure induction, as it were.
And that can be used as a generator as well. Yeah.
Yes. Yeah.
Is there any way of firing one up?
Yeah. So I've got one here. We can wire in series or in parallel. So the thing with a universal motor, it can also be used in DC.
Right.
So in the DC world, we've got a series wound motor and also what we call a shunt wound motor. So that would be a shunt or parallel connected motor as well.
I'm not seeing slip rings this time now, am I, here where we're making a connection? What am I seeing this time?
So this is a commutator. Okay.
Right.
So each one of these segments is actually isolated from one another, and they represent one single winding within this field winding. So it's important reference there. Keyword on this particular motor is that the stationary part of the motor is actually called a field winding.
Okay, and is this working on AC or DC?
This is working on DC.
That's it. And can we tell that from the fact it's got a commutator on the end there?
Yes.
Okay, so when we're looking at ones with slip rings, we're working on AC, and when we've got a commutator on the end, we're working on DC, yes?
Yeah.
Okay, I've remembered something.
We can also use, when we start talking into the worlds of universal motor, the concept that this motor is connected in series, it would work in both AC and DC.
Okay.
So there we go.
Okay, good.
Right, so I'm going to fire this up.
Oh wow, there we go.
The interesting thing in DC with this, the way that this is connected in series, is that the speed referencing will just increase and increase and increase. So this motor behaves better when it's actually under loading conditions.
Right, and that would be under a constant load, would it?
Absolutely, yeah. So whatever it is mechanically driving.
Can we just see that once more? Just see that far up, and I'll just slowly pan across it so everyone can see all the parts. So there we see the commutator. As we come down there, we see the shaft of the motor on this end spinning as well. Yeah, cheers, Pete.
Awesome.
So there's an interaction there between the magnetic fields, is that right?
Yes. The commutator acts as a pole shifting device, certainly in the DC world area of it. And what it's actually doing is changing, because in DC we've got current travelling in one direction.
Yep.
The commutator assists in creating it almost like a hypothetical synthesized AC.
Right.
So it would direct current in different directions to create that rotating magnetic field.
Okay, thank you.
Looking a little closer at that,
Okay, yeah.
you can see the intricacy of the windings, and also the commutator.
And each one of those windings you said come back to the commutator there, so we're actually going. They all look like they're touching each other, so that looks like there'll be a dead short everywhere. So what's happening to the windings?
So each one of these, believe it or not, has got a little insulative mica in between each one. Okay, so they're not actually touching one another, but the brushes will sit, enabling lubrication. Yeah. Okay, and also it's a soft material. It's very good conductor. But that's obviously a disposable part, so you've got some real maintenance consideration with this kind of motor to think about.
And the windings themselves look like they're sitting on top of each other as well, so they look like they're touching. So what is happening to the copper windings to make them not short together? Yeah,
that's interesting, because all this copper wire here looks like it's shiny, metallic and bare conductors, but it's not. It's actually got a shellac or varnish over each one of the conductors, so they are insulated from one another.
Would you call that laminated?
Laminated, yeah.
Yeah, that's sort of exam question comes up, isn't it? They cause are laminated from each other.
Yeah.
Right, okay, brilliant.
Of course, key wording is very important.
Yeah. Where are we next then?
Okay, so when we start to look at pure induction motors now, so we've had a little bit of a look at induction on the rotor wound motor, but this concept with the Nikola Tesla squirrel cage motor, it actually hasn't got an electrical connection to its rotor. Okay. So if you remember, in the universal motor, it was called an armature. Yeah. So in a pure squirrel cage induction motor, it's actually called a rotor. And the windings for that, or the stationary part of it, is actually called a stator. So perhaps a little bit easier to remember in AC motors, these key words, as it were.
Okay. A bit concerned, because that don't look like it's made of something that's easily magnetised. That looks like it's made of aluminium. Have I got that wrong?
No, it is aluminium, and it's non-magnetic. So you would think, I'm
going to get an interaction here.
Absolutely, it's got no electrical connection, and also, as you say, it's non-ferrous. So how does aluminium react, and how does this become a rotating part of the machine?
Well, I'm intrigued. I'm sure Nikola Tesla got it right. Have you got anything you can show me as that as a mini experiment?
Okay, absolutely. So the concept of a squirrel cage induction motor. Now, called squirrel cages because you've got bars that pass through the rotor, and they are shorted out with these plates or these parts at the end here. Okay. So it's more like a hamster's wheel than a squirrel cage, but I suppose hamster's wheel weren't invented 100 years ago. Okay, so there's a little model there as well, just demonstrating there's no electrical connection. Okay, but the concept is that if you have relative motion, a magnetic field, and a good conductor, you can in fact have a motor.
Okay.
Okay.
So this is an aluminium disc. This looks. I don't want to jump in here, but that's got a whiff of a fidget spinner about it on the back there.
2007. My son will be proud of me.
Okay, so it was a family heirloom, and now it's part of an experiment.
Yeah. Okay. So and interestingly, just to demonstrate there, we've got no magnetic interaction with the aluminium disc.
Yeah.
Okay. So what I've actually done here is I've pole shifted in terms of north and south with these magnets that are mounted to the fidget spinner. Okay. Okay, so the concept, relative motion, a magnetic field, and a good conductor. Yep. So bearing in mind the aluminium part of it is the good conductor. I've just got to apply the relative motion, and in doing so...
Oh, wow.
we get the interaction.
Yeah, aluminium is not magnetic. So
No.
was it inducing an EMF? Have we got
Yes, absolutely. So we're actually setting up a very real current inside the good conductor on this side. Interestingly, with the motors that we've seen previously, the universal motor, we could use that as a generator as well. But in this concept, it doesn't. It falls apart. So demonstrating the relative motion of the rotor to try and get the magnetic part to spin wouldn't actually work.
So is this similar to how the old electric meters used to have an aluminium disc in? Is it using a similar sort of principle, or have I got that wrong? The old where the disc spun round.
The disc spinning round,
yeah. So that was the way they were working similarly?
Yeah.
Could we show this then also? Can you sort of liven up a motor and we see this in
Yeah,
principle?
absolutely. So here we have our rotor.
So that's aluminium, yes?
That's aluminium, yeah.
Yep.
Okay. It has got some laminated cores to it, but I think we should ignore the fact that it has got some steel to it.
Okay.
Okay, so that's transformer theory in terms of providing a permeable to assist with and encouraging that magnetic field. But in essence, what's actually happening, the interaction on its own is happening between the windings, or the stator in this concept.
And that creates the magnetic field?
Yes, and also we need that rotating magnetic field. So we've got to create that rotating magnetic field with the rising and collapsing of voltages and current. So what we've got here is each one of these windings would be directing the current in a different direction to create a rotating magnetic field.
Okay, so you set your poles up before, you set them not all up in the same direction on our little practice one there, you set them up differently, and it's exactly the same here but electrically.
Precisely, so what we've got to have is north and south poles.
Yes.
Repelling and attracting, and what we're in fact doing, we've got to set up that new EMF inside this rotor. So demonstrating, so we're nice and safe here. It's 50 volts, 3-phase. So
but it's isolating transformer, so there's no risk of shock to earth. Yeah. Okay. I'm sure people have done that as well in their studies. So we're going to get this to spin. This is exciting.
Okay. So, I'm going to just energise this up, and we'll be able to see and demonstrate this actually working.
Oh wow. So obviously rotating magnetic field, inducing the EMF into the aluminium and causing it to rotate. But you said this can only be used as a motor?
Yeah.
And the advantage being, was this quite an inexpensive machine to make, is it?
Well, thinking about the intricacy and cost element, and also the maintenance behind an armature, you can see pound for pound really that the rotor is going to be greatly cheaper to produce. And the fact that we've got no brushes or electrical connection, the cost, so cost of production and also the maintenance.
So when we think about carbon brushes, they wear out over time, don't need replacing.
Absolutely, yeah.
So we haven't got that. That's fascinating, absolutely fascinating, Pete.
So paying reference there to Nikola Tesla's squirrel cage induction motor.